Hey, George, you're a scientist.
I'm a chemist, yes.
Right, you're a scientist. So I have worked in tech for my whole career. You've been in science for your whole career. And I've started seeing people use the term smart plastic. And in tech, smart usually means we shoved a computer into it, right? So like a smart TV, a smart car, like smart appliances, right? It usually just means we took a thing that was done analog and we shoved a computer up its butt. And that marketing kind of caught on from like smartphones, but smartphones were already technology and now they do more technology stuff, right? So like I'm hoping, I'm praying a little bit that like that's not just what people mean with smart plastic, because that would be lazy. So what does it mean for a plastic to be a smart plastic?
Well, darn it, Lions. I'm an analytical chemist, not a polymer chemist. But with my very limited knowledge and very limited expertise, I will attempt to opine to this. So let's start off at the top of the hour. And I do apologize because, I've been learning a lot in some of my chemistry courses. And so a lot of these subjects have been circling around that. But the upside is that, you're going to have a lot of this grilled into you by the time it's all said and done. So top of the hour, because these are evergreen episodes, what is a plastic?
So plastic is like a chain of like identical molecules, right? So you've got,
Yep.
or I guess they have to be identical for it to be like a uniform plastic.
No.
They have to be identical at some repeating pattern size. You wouldn't just have
Yes.
random bits that were
Well, so
like a chocolate chip cookie is not perfectly uniform, right? But
well, so technically it's a polymer if it is a long chain of organic molecules, right? Is technically what you could classify it as. What we would consider it would be a long chain of repeating units,
Yeah.
But technically DNA is a polymer,
Yes. Okay. I see what you're doing, and I appreciate
Yeah.
your gumption for precision.
Yeah. So technically that's true. However,
Yeah.
if you were to talk about polymers and somebody said DNA, saying DNA is a polymer is like saying GLaDOS and Portal is a first person shooter, where it's like you are technically correct, the best kind of correct.
Yeah.
All right, let's all move on.
Portal at least had a gun. It still broke my brain when we realized that Pokemon Snap is an on rails first person shooter. That's so good. That's not what those words mean, but it is technically true. You did say an important word that I left out though, which is organic, meaning carbon.
Yep, exactly. Yeah, because inorganics don't polymerize like that. So one of the cool things that you can do,
I bet there's a science fiction thing about like an inorganic polymer, because that feels like the kind of thing you would say makes the magic technology in your book possible. And my go-to example for that is in Star Trek 4, one of the early ones, when they have to like teleport the whales. And they're like,
transparent aluminum.
Transparent aluminum. Yes.
Yep.
That's such a thing. Like, to an idiot like myself, like that just sounds like, yeah, that would be really useful. And to someone who's like a metallurgist, they're like, what are you even talking about?
Well, especially for people who really, really would know about it, they'd be like, how would you even do that? Like how would that work? But what I'm learning a lot of with polymers and stuff is that, and by extension plastics, is there is basically plastics was our key to the what if we were God, because the amount of stuff we can do with this is like, because before it was like, oh well, we have to use a metal and metals have certain properties, and oh well we can make some small chemicals and they have certain properties, but like we can't really change them too much. And then we started making polymers and we're like, oh, we can kind of tweak this however we want to do whatever we want. And it gets pretty wild. One of the things that you can do is create something called a block copolymer, which actually, when you said, oh, it's all the same thing, is I'm like, no, and it's going to come up real soon. That's not
matter of fact.
Yeah. So a block copolymer is if you've got polymer A and then polymer B, is you've got A, B, 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 A, and they come off in like chunks. So the reason why you would do that is because you want it to have some properties of thing A and some properties of thing B. And then when they kind of, work together, like they will do weird and interesting things when they're brought together. So to answer your base question, right, and then I will go into some examples of this to flesh it out a little bit. What are we saying when we say something is a smart plastic? We are saying not that it has a computer chip in it, because, when you're dealing with plastics, the computer chip would be like having the planet Earth smashed into it, because, the microchip itself is so much larger than the polymer, So what we're really saying is it's a stimuli responsive polymer, So
okay, so this is starting to sound like, oh, if you put a charge through it, it'll magically take a certain shape, like that kind of. Mm-hmm. Yeah.
Yep.
Okay.
Yeah. So basically, the idea is that like if you do environmental thing X, it will behave in way Y in a very controllable way, which means that you can do all kinds of like weird and interesting stuff with it. So basically, and so it seems smart because it's like, oh, well, it can sense when the temperature becomes A. And it's like, no, it doesn't. Just physics determines that when temperature becomes thing A, it then behaves differently. We, the actual smart thing, built it in such a way so that way the intermolecular forces or entropy behaves in exactly a certain way. So it will do very specific things. So that's what a smart polymer is it just reacts to the environment. And normally it can only react to the environment like one way. Like it's got one trick, So, but that being said, is some of the smart polymers can do insanely cool stuff. And now we're going to talk about it. So one of the cool things that a smart polymer can do. So let's talk about a pH responsive smart polymer. So for our listeners at home, what is pH?
It's the measure of acidity. So
yeah,
you have, I think 7 is neutral. Mm-hmm. And then I always mix these up. So I'm just going to flip a coin and see if the luck comes up my way. Lower numbers, more basic. I mean, it was 50-50, right? It was. Yeah. So 7 down to 0 would be your more acidic. So lower number would be more acidic. And then 7 up would be more basic. So technically, if something goes from 13 to 12, you have made it more acidic, but it is still basic.
Yeah. A way to maybe think about it is that
alkaline actually the right word there?
Alkaline, yeah. It is a base, so calling it basic is also fine. But yeah, you could also say it's an alkaline solution. So a way to think about it is like, man, trying to collect numbers and just making the numbers go higher, man. Like I remember when you and I were younger, we loved watching the numbers go higher. That's so basic. So higher basic.
Good. I like that. Unfortunately, will stick with me. So thank you.
Yep. And then people will be like, "How do you remember that?" And you're like, "I don't want to say." I want to talk about it. So, what it basically acidity and alkalinity measure a compound's ability to, or a solution's ability to donate or receive a proton, respectively. Right. So, more basic things are ready to receive protons, and more acidic things are ready to give those protons away. So basically, so let's put a pin in that thought. Do you know what a micelle is?
Nope.
Nope.
that one. Nope. I mean, I'll spare you the obvious joke of the wordplay there, but just no, I don't.
So basically, what a micelle is when you've got a molecule that has 2 different properties. One of them is hydrophobic, and one side is hydrophilic, right? So
rejects water and takes in water.
Yep. Yeah. Or likes and dislikes, right? Yeah. Phobic, scared of dislikes, and then philic, likes, right? Just realized that I was going to say like, oh, well, phobic, like as in a phobia, and philic as in like a. Never mind.
But yes, like
apparently it was like there's one place where our language uses that a lot, and let's all just move on. So I say that to say that what'll happen is if you've got something that so if let's say you've got something that has a long hydrocarbon chain, hydrocarbons mix or don't mix in water.
Do not,
right? Yeah. Oil and water don't mix,
oil and water
right?
Don't mix. Yeah. We talked about
so you got a
this
long
once.
hydrocarbon chain, right? And you dump that in water. It does not mix, right? But if you put something that is hydrophilic on the end, say like a carbonate or a sulfate group, that likes water. So if you put a whole bunch of those things together, what'll happen is all of the hydrophobic tails will all point in towards the center to try to get away from the water and be near each other. And all of the hydrophilic ends will all point towards the outside because they're totally cool with being in water. And that is a micelle. It's basically a ball, where you've got hydrophobic stuff on the inside and then hydrophilic stuff on the outside. It is, interestingly, how soap works. So,
oh yeah, I've seen, because soap, like, it doesn't like destroy the dirt. It encapsulates it, and then the water washes the soap away that has the dirt encapsulated.
You got it, man. Yeah, absolutely. Yeah, which is kind of cool, which is actually why if you look at your soap container, I bet you that they will probably say something like sodium lauryl sulfate, right? So the sodium is the positive ion, the sulfate is the negative ion, and lauryl is the, big hydrocarbon thing on the end,
Yeah,
and then everything else is
Yanni.
Yanni?
Oh man, I thought for sure. I was like, there's no way he's going to get this internet reference. I'll leave that up as an exercise for the readers, but I will show it to you after the recording is done.
Got it. So anyway, so that's what a micelle is. So one of the other interesting things about a polymer is that when you think of a polymer, right, it's a long hydrocarbon chain, right? As we just said, right? No, wrong. So what they tend to do, which is actually, I think, because I never really thought about it, is that like imagine you've got a chain. A whole bunch of links in a chain, right? Now, if you pull them all taut, right, there will be a long linear chain, right? But most of the time, when you see chains just lying around that aren't intentionally pulled taut, are they in a line?
No, otherwise, like Christmas lights wouldn't knot up, right?
Exactly.
They don't tend to sit in their completely straight state.
Yeah, actually, Christmas lights is a perfect example, right? So hydrocarbon chains do the same thing because those bonds can rotate around each other. So when they're perfectly what's called trans, right, they form this chain. But all it takes is a little bit of rotation, and now you've got a kink in the chain, and another kink, and another kink, and another kink. So they tend to form these kind of like viscous like balls, right? Specifically, what you can do, though, is if you create a block copolymer that has the right ratio of hydrophobic and hydrophilic nature, you can get it so that way it forms micelles at certain pHs and then forms more of a long chain at a different pH, right? So one of the things that they can do with this concept to make a smart polymer, which I think is so cool, is for drug delivery. So what they do is they created, there's many polymers that can do this now, but the one that I researched in preparation for this is they created a polymer that forms a micelle at a pH of greater than 7. And it forms a kind of a long, spaghetti chain at pHs less than 7, right? So what they do is then they take they take the drug, right, and they put a bunch of the polymer in it, and then they bump up the pH. So what happens is the drug, which is organic, right, seeks the inside of that micelle, so the micelle just gobbles it up like Pac-Man, right? So now it's now encapsulated in that plastic and will not do all of the chemistry that it could do. It is protected. It has its shields up, right? So then what you do is you inject it into the bloodstream. And just out of curiosity, do you know the approximate pH of blood?
I'm gonna extrapolate from information here and say it has to be slightly more acidic than the environment that was created in. So I'm gonna guess maybe like 5, not super acidic.
Yeah, so I like your reasoning. It's actually at 7.4.
Slightly basic.
Slightly basic, yes.
Okay.
It's slightly alkaline, and actually, blood is one of the like most buffered, naturally occurring solutions. Like
Sure.
It is at 7, and you can put a fair amount of acid in there, and it'll still stay at 7.4, and it'll stay there because it's really important for all of the chemistry that your body does. That your blood pH is exactly 7.4.
Yeah. Whatever it is, that's what it needs to be. It could be, It could be 2, it could be 9, it could be 14, but that's what it needs to be because your blood is sort of involved in everything.
Yeah, in a lot of stuff, right? Because the thing is that they don't want the drug to be in the bloodstream. If they did, they would just inject the drug directly in your bloodstream. What they want it to do is to release directly into the cell. And so what happens is it goes through your bloodstream. It is still encapsulated because the pH is higher than 7, right? And then it gets into your cell, and your cell goes, oh crap, an intruder. And what one of your cell's defenses when it sees an intruder is it throws protons at the problem, because throwing protons at the problem a lot of times fixes the problem, right?
I like thinking about that on the macro scale. Is like somebody comes into your house, so you start throwing things at them to try to make them stop, right?
Well, it's kind of like when COVID was rampaging and people were like, well, why don't you just, why don't we just use this or use that? And it's just like, I mean, like, why can't we figure out a way to kill this virus? It's like, well, I mean, sulfuric acid will kill it. It's just, it'll kill you too, you know? So
it's killing the virus and the host surviving to live a life worth living. Like, that's the sweet spot.
Yeah, and that's hard. But if we're just trying to kill the virus, I mean, a small amount of lead propelled at a great speed will get that job done, So then what happens is when the cell starts throwing protons at the problem, right, is it acidifies the area, which again, like for viruses and for other things that are trying to intrude into your cell, will cause problems and break them apart, right? But with the micelle is it causes the micelle to open up, and it delivers the drug directly to the cell, which is awesome, right?
That sounds, because I mean, it's impossible for me, a human being, to not picture this on like a macro scale, right?
Right.
Like, it's just, when you're in high school and middle school, like that's what science is shown like, is like, here's the cell, here's DNA, and everything looks very like, solid colors so you can learn where the structures are and everything. But also, like, that is literally what's happening. We are literally saying, like, well, then this thing gets absorbed by the cell, and then it unfolds, and then the drug is released into the cell. And it's like, oh, well, is that an oversimplification? It's like, no, that is literally exactly what's happening. It was just really hard to figure out how to do it.
Well, and I think that it's interesting because a lot of this sort of stuff kind of goes to one of my philosophies, which is like, every problem has two possible solutions: change yourself or change the universe, right? So a lot of the cool science stuff is people way smarter than me saying, I don't like this, but here's how the universe works. Can I twist that to my advantage? Like, most scientists are like, basically are looking at the handrails of nature and seeing places to grind their skateboards. Like,
yes, this is, and this is, I don't know, maybe what a official term for this would be, but like, it's like a someone who's doing pure science where they're just generating the data. Like, hey, if you do this, this is the result you get. It's consistent, it's predictable, it's reliable. Check my math. And then you have someone else who's like, I could grind that rail, right? And like, you need both of those people, because those are both full-time, super hard jobs. You need the person who's like, okay, I'll pour the concrete like this, and I'll put the rail like this, and then it'll be there, and people will be able to use it for something. I don't know. Maybe they'll put their hands on it. And then someone else is like, I could grind that rail. And it's like, good. Okay, that is not a use that this person originally envisioned, but I'm super glad you're going to do that with it.
Absolutely, right? One of the other ones that is kind of interesting is they have salt responsive polymers, which so other things like you can use light, you can use temperature, and there are examples of all of these. I picked the two that I thought were the most interesting, and also, to be honest, the two that I understood the best. So
it's fair. But, as you said, this is not your area of scientific expertise.
Exactly. No, I am. If I had to gauge it, I'd say on a scale of like, weeks, I probably have about 10 to 11 weeks of experience in this area, as opposed to my 15 plus years in analytical chemistry. But that being said, let's talk about salt for a minute. And plastics in general. So plastics can have variables.
You need to know that the way you phrased that sentence made it sound like salts are plastics. And for just a second, I was like, no, salts are not plastics.
Salts are not plastics. Salts are salts. Plastics are plastics. Math is math. So plastics can have varying solubility, right? So solubility is
its ability, the material's ability to dissolve into water.
Yeah. Yep. Actually, interestingly, it's the thing's ability to dissolve in another thing. typically water, you know?
Sure. Yeah. Like when
Yeah.
people say ice, it's not necessarily water ice, but that's usually what we mean.
Yeah, exactly. When you say it's soluble, there's a 95% chance that you're talking about water. But like sometimes you could be like, is it soluble in methylene chloride? Because that's what I'm trying to use, you know?
Right.
Yeah, is it soluble in this organic solvent? But that's normally like scientists talking about that. When we're talking about solubility, we're like, hey, if I pour a bunch of salt in this thing, how soluble is the salt? And chances are you're not pouring it into methylene chloride.
I'm making a cocktail.
Well, you're definitely making a cocktail, but so I say all that to say that they do have varying solubility in water, and the way that you can tune that is by picking your polymers and picking your ratio of your block copolymers. So do you do AA B B B B B B B B B B B AA B B B B B B B, or do you do AABB AABB? You know, and then you can say like, okay, well, I want this to be more soluble, so I'm going to use more of the water soluble, you know, polymer. And you know you can tune that characteristic, right? But water. So interestingly, the way things become dissolved in water is basically the water is like the bouncers trying to break up a brawl, right? So water, you know, if you pour a bunch of sodium chloride into a thing, it's all together, and water goes, hey, whoa, 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 here, I will hold on to you. Right, and I'll put all of my water molecules around you and hang on to you, and then keep you separated, and that's what keeps it dissolved. And then when all of those areas are locked up, that's when it's saturated, and the salt just kind of pours through. Right, the same thing with polymers. But one of the things is that those spaces, right, because there's only so many of them, they're highly competitive, and so salt will displace something that is less soluble than that salt. You know. Because the water basically says like, oh, hey, man, I'm cool with grooving with this polymer. This polymer is pretty neat. Like, I don't love all of the polymer, but I like the part that I like. And, you know, we make it work. And then all of a sudden, salt comes in and 300 kicks the polymer out of solution, right? And thus you can have salt that displaces a polymer. So what they are able to use this with, which I think is very cool, is they can take like a disc and graft polymers on top of it, right? And so when the water is just, you know, water, there's nothing else in it, those polymers become wacky waving inflatable arm flailing tube man, you know, they're right, and they are just having a good old time. The water and it are jiving, they're having a good old time, right? And then salt comes along, water's preferred partner, and the salt kicks the polymer out of the solution. What that effectively means is that this long polymer chain is now pushed against the thing that we grafted it to, this plate, you know? So it kind of becomes, you know, kind of like all deflated and sad, right? So they can make valves out of that, because when the salt hits it, the valve opens because these things compress down and it lets everything through. And then once all the salt passes through, right, and it cleans out the system, then they go back to being wacky waving inflatable arm flailing tube men, and it can close the valve. So you can literally create nanometer sized valves by using these plastics as open and closing, and they just do this naturally because it's physics. You know, they will never not do that.
So are there, first off, I am still struggling to not think of things at the macro scale. So I'm going to ask you, like, are there macro scale, and any macro scale examples you know of? Because I was imagining with the injection that feels like a thing that you could hypothetically do with like a pill, right? Is I have a pill, and the way that the drug will be, like, I'm imagining like you have a drug that you want to be delivered in a specific part of the intestines. And if you know, or the digestive tract, and if you know, like, well, the pH is 4 at this part of the digestive tract, then we need to make something that can survive the earlier parts of the digestive tract, but then will open up at this later part, right? And so like it's the same kind of delivery mechanism. It's just on like that kind of more macro scale where it's like I could see the pill, like I could see the polymer part, and the drug part is inside and I want it, but it's not just, oh, this will dissolve in your stomach, because maybe dissolving in your stomach would be bad. It needs to dissolve like in your large intestines or whatever. And so like, are there, do you know of any like macro scale examples like that?
I mean, what you just listed would be a perfectly good.
Okay, good.
It would be a reasonable application of that, right? Is that basically is, you know, like when you say, hey, I want this drug to be delivered under these conditions, then you would just tailor the polymer so that way it opens up under those conditions, you know? The only problem that you could potentially run into in that particular case would be like if, for example, let's just say that you've got your stomach acid, which is a pH of like 1 or 2, and then it goes to, let's say, your large intestine, which has a pH of, let's just say, 7, and it goes to your small intestine, which has like a pH of 10. Or sorry, let's say, excuse me, let me flip that. So pH of 2, pH of 10, and then a pH of 7, and that's where you want it to release. That would be tough because you need it. It's going to transition through those different pHs. It's just going to open up whenever it hits its sweet spot, So like,
right.
That would potentially be difficult, but realistically, if you're like, hey, everything is going to be acidic until it hits the place where I want it to be, where it will be basic, then Yahtzee, And actually, too, like there's a whole bunch of different like other, as far as like macro scale applications. Part of the reason that some of this stuff is so cool is because we can tailor it to be so small, I mean, you could even say like, if you're like, hey, I want this molecule to become more viscous in clean water in fresh water as opposed to salt water, right? So then what you could do is you could literally create this polymer, right? And then create like basically bristles on the end of it, like a toothbrush, And so then those two, if you make it long enough, right, then when the salt is there, it would kind of collapse down and have less entanglement. And then when the salt isn't there, it would spread out and like get in each other's way and become more viscous and more entangled, So like there's all kinds of, again, for people way smarter than me, like all kinds of like wild applications you could do with this. But basically is when you say, hey, this thing, and what they would say for like the salt thing, for example, is like, this thing's hydrodynamic volume is greater when there is fresh water and smaller when there is salt water. Do whatever you want to with that, like I got a thing that on the very, 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 very small scale shrinks. And one of the other cool things that they can do with this stuff as we're talking about it is, so oil and water don't mix, right? You get what's called macrophase separation, right? So that's when you have two incompatible things that are trying to share a space, right? What you can do, though, is you can, in a polymer, graft those two things together and make them play nice. And then you get what's called microphase separation, where they still try to separate from each other, but because you grafted them together, they can't as much. And the analogy that my professor used, which I really love, is that macrophase separation is the chocolate chunks in a cookie. Microphase separation is if you ground all of those up and put them in the cookie. So you still get these separations, but it's on the nanometer scale as opposed to the millimeter scale. And again, that you can then create all of these different, they will then try to form different structures based off of their concentration, based off their solubility parameters, based off their pH, based off all this sort of stuff. So you can get a bunch of little balls, or you can get these clean sheets, or you can get sheets and then sheets on top of sheets. And then you can use those structures to then build different things.
Well, I do like the idea of it is definitely easier to reason about in like a, and then the polymer walks up to the cell door and asks to come in, right? And it's like, yes, it's just, we're human-sized humans, so it's easier to think that way. But I'm doubly fascinated by people who can take something happening at that scale and consider the emergent properties on the macro, because sometimes it's not the same, right? Like saying, oh, this thing behaves this way when there's one of them and it's a nanometer long is not necessarily then, if you have a trillion of them, it'll do, like, it's not necessarily linear where it's like, oh, now it's a trillion times more. It's like, no, it might be quadrillions of times more because there's like a compounding effect or whatever, right? So like not only how would you use this thing at this scale, but then when you scale it up and down in quantity or in like surface area or volume or whatever, then how does that have like weird kind of emergent properties? And then you have to, I think, come up with continually stupid metaphors, right? So if like if you're the polymer like going into the cell and then getting like protons thrown at you, so then like on a macro scale, it's like, I don't know, like an invading army like crossing the border and like getting shot back at like No Man's Land style from the foxhole. Like you have to keep scaling up your stupid metaphor to go along with the size of the impact of the science, because if not, what are you even doing?
Yeah, no, agreed. And definitely coming up with those metaphors can be cumbersome sometimes, because it's like, oh, it's kind of like this. And it's like, oh, so it works. It works like that. No, it a little bit. But one of the things that and to kind of button it up a bit, right, is that when people refer to smart plastics, is is they're like, oh man, smart plastics, that's amazing. It's like, I actually prefer stimuli responsive plastics because smart people can change the way they behave. Stimuli responsive plastics do not. They will always behave the same way every time. They will never, the plastic isn't smart and could make a different decision. It is not making a decision. It is reacting to physics. And that is way more predictable than something that's smart.
Well, and in this way, it does bring us back full circle, because that is a lot like technology where we use the word smart. It's like, no, it's not smart. It's a thing with a computer in it. Like,
yep.
what you have is a thing with a microprocessor in it, and these plastics are not making well-reasoned decisions. They are responding to physics, which reminds me of some other materials I wanted to ask you about.